All right, hello everyone. I am Jonathan Mace. My advisor at Brown is Rodrigo Fonseca, and today I will be talking to you about context propagation in distributed systems. So context propagation is an important component of many tools that monitor and enforce distributed system behaviors. But context propagation requires significant time commitment from developers who have to go and instrument their system's source code to propagate contexts. So in this work, we generalize and abstract context propagation so that it can be shared and reused by different tools. This drastically reduces the effort required to deploy new cross-component tools in distributed systems. At the heart of our solution are baggage contexts, a general-purpose serialization format that provides a key property, and that's the ability to merge two serialized context instances into one without having to interpret the serialized data. This property is what enables us to decouple context propagation from the tools that use it. So to start the talk, I'm going to take a step back and just give you a quick look at the broader setting. So the distributed systems that we're all used to are by their nature quite complicated. So individual systems internally comprise many interoperating processes, and at the same time, we design our systems to compose and interoperate with one another. So ultimately, a high-level execution from a user, such as a single API call, a processing pipeline, or a data analytics job, is going to involve multiple processes, components, and systems. It'll have multiple hops over the network, and it'll do concurrent work across multiple machines. Many problems can arise in this setting, and in the past decade or so, researchers have proposed various tools and techniques for tackling them. In this work, we focus on a particular class of tools that we term cross-cutting tools. These are runtime tools for distributed systems that coordinate across the boundaries between components. And they do this using context propagation. So I'll show you an example of how context propagation works by illustrating a distributed tracing tool, which falls into this category of cross-cutting tools. So you might already be familiar with distributed tracing tools like Xtrace, DAP, or Open Tracing. The goal is to combine logging statements, or events, across all system components. To do this, system developers will modify their system source code at various points to emit logging statements. At runtime, when an execution reaches these points, they will emit events that are aggregated by the tool's backends. And this is done across all system components for the end-to-end execution. I think this has started to die. All right, so these events, this gives us the events, and from here we need two further things in order to construct a trace. First of all, there could be concurrent but unrelated executions, and we want to separate the events related to each individual execution. Then second, we want the order and causality between events because of internal concurrency within executions. To get these things, we record additional information at runtime, and this is where context propagation comes into play. At the start of an execution, the tool will assign it a unique execution ID. This ID must then be propagated alongside the execution wherever it goes through all system components. That way, the tool can then annotate every logging statement with the execution ID. And then the backend can distinguish between events which belong to each execution. To then get the causality between events, we need to go a step further. Whenever an event is generated, it's assigned a unique event ID. Then, in addition to propagating the execution ID, we'll also propagate the ID of the most recently seen event, or predecessor as it's labeled here. We update this predecessor whenever we generate a new event. Concurrent branches of execution can therefore have different predecessors, as they're essentially independent from one another. If concurrent branches at some point rejoin, then they'll retain both predecessor IDs, as shown here. So using this, each event can explicitly record its immediate predecessors, and then using these predecessor IDs, the backend can construct the relationships and ordering of events. Now that was a really quick description of distributed tracing and how it uses context propagation. But this example shows how propagating contexts with executions is useful for communicating information across components. Beyond distributed tracing, there are a wide variety of tools that do different tasks and propagate different kinds of metadata. So for example, there are tools for scheduling, latency, and resource management. They propagate things like tenant IDs, latency measurements, and critical path estimates. Instead of logging events, they use this data at runtime to coordinate throttling and scheduling decisions. Other tools for metrics and monitoring will dynamically propagate tags, identifiers, and tuples that they use for grouping and filtering metrics across components. There are many other use cases besides these, and in general, different tools will propagate different things, ranging from simple static IDs to more elaborate dynamic data types that get updated during the execution. Now, despite the differences between tools, they all share one thing in common, and that is the need to do system-level instrumentation. Because actually propagating contexts requires developers to go and modify their system's source code at all execution boundaries. So for example, contexts have to be explicitly retrieved from RPC headers, then stored in, say, a thread local variable. If new threads are created, contexts have to be copied for the new thread. They have to be serialized and included in RPC headers. They need to be included through any queues, continuations, event callbacks, asynchronous communication, and so on. In all, instrumentation entails pervasive modifications to all system components to make sure that contexts are propagated with everything an execution does. And it's required for all components, otherwise the context could be dropped partway through execution. All cross-cutting tools require instrumentation for propagating contexts, and that requires significant time and energy from developers, and is easily regarded as the biggest cost in deploying cross-component tools. Moreover, all cross-cutting tools to date entangle context propagation with other elements of the tool, which inevitably leads to instrumentation that cannot be reused or shared with other tools. So to go and deploy a second tool will mean revisiting all of the instrumentation for context propagation. And that's a huge obstacle. So our contribution in this work is to generalize the context propagation piece of these tools. That way, instrumentation for context propagation is only done once, in a general way, and thereafter cross-cutting tools can share and reuse instrumentation to propagate whatever data they like. Doing this requires a flexible intermediate data format, and that's the role of baggage contexts. They give us a concrete underlying implementation to bind our systems to at development time, and they're carefully designed so that they can represent any data types that might be needed by cross-cutting tools at runtime. Those internal details of baggage contexts are not something that we would want to expose to cross-cutting tools directly. Instead, we provide an interface definition language called BDL, or baggage definition language, for specifying the data types that we want to use in our cross-cutting tools. The BDL compiler produces the code for interacting with baggage contexts, hiding the underlying data format. Overall, this forms a layered architecture that we call the tracing plane, that separates the concerns of cross-cutting tools from system-level instrumentation. This separation has a huge benefit. Previously, someone deploying a cross-cutting tool would have to juggle several skill sets that have to know everything from the underlying system all the way up to all the elements of the cross-cutting tool. By separating these things, we also separate the skill sets needed for each task, providing a lower barrier to entry for deployment. So I'll describe some of these layers in more detail, starting with the system-level instrumentation. So instrumentation for context propagation is encapsulated in what we call the transit layer. System developers instrument their systems to propagate opaque baggage context objects using an API of 5 propagation operations. Of these, serialize and deserialize simply convert baggage contexts to and from a wire format. Branch is used to derive new context instances when executions split into concurrent branches, since each execution branch requires its own context copy. Merge is used to combine two incoming baggage contexts into one whenever concurrent execution branches rejoin. And finally, trim is used to impose a size constraint, but I'm not going to get into this in the talk. So that's all we need for instrumenting systems. All of these operations treat baggage contexts as opaque objects, so that instrumentation isn't bound to the data of any particular cross-cutting tool. If we now move to the topmost layer, here cross-cutting tool developers simply specify what data types they want to be propagated for their tool using BDL. BDL specifications can use a range of different data types, including primitives, nested data structures, and more. As an example, our earlier tracing tool propagated an execution ID and a set of 0 or more predecessor IDs. So in BDL, we would specify an integer execution ID and a set of integer predecessor IDs. We give the names, types, and a positional index for the fields that we want to propagate. We can add new fields and deprecate old ones without affecting compatibility with prior versions of a tool. This looks and behaves a lot like protocol buffers, but there is a key difference that I will describe momentarily. So from a BDL specification, tool developers use the BDL compiler to generate accessor interfaces. The tool can use these to get and set variables from baggage contexts. So for example, setting the execution ID and adding a predecessor would look something like this. The intervening two layers define baggage contexts and provide the bridge from instrumentation to those elaborate data types used by cross-cutting tools. The first of these layers, that we call the atom layer, provides a concrete underlying serialization format, as well as concrete implementations for each of the 5 propagation operations. Then on top of that underlying serialization format, the baggage layer specifies encodings for BDL data types that map down onto the atom layer's serialization format. So in order to support nested data types and to multiplex cross-cutting tools, the overall representation of a baggage context ends up being a tree. The nodes of the tree are used for addressing, and the values of data types live at the leaves. We'll come back to this in just a second, as I'm going to go a little bit further into the details of these inner layers. But I won't go all the way to talking about the bits and bytes of the actual serialization format. For all of those gory details, I'll let you take a look at the paper. So recall the 5 operations that system developers use to instrument their systems. Of these, serializing and deserializing are trivial, and branching simply involves duplicating the context, 1 copy for each branch. The operation that makes everything tricky is merging. Merging significantly impacts our design at every level. Concretely, all BDL data types need well-defined merge semantics, because we need to know how to correctly merge 2 instances of a data type whenever 2 branches of an execution join. We want to make sure that we combine them in a way that makes sense for the data type. For example, our set of predecessor IDs has a somewhat natural merge operation of a set union. If there are 2 different baggage context instances that have different values for a predecessor ID, then what we want is to take the set union after merging. I also just mentioned that we represent baggage context instances overall as a tree. So if we had this baggage context with an execution ID and a predecessor, and we wanted to merge it with this one that just has a predecessor, the desired merge behavior of a tree will extend in a similar way. We want to match the nodes of the tree based on the node's ID and recursively merge their children. If a node only exists in one of the input baggage contexts, then we would retain that node and all of its children. When we reach a leaf, we want to merge based on the data type of that leaf. In this example, we would do the set union of predecessor IDs that we just saw. Many of the ad hoc approaches to context propagation used in existing systems today do not sufficiently handle merging and trivially fail to correctly preserve data types through merges. So merging then also makes the design of the underlying serialization format tricky. We need a single underlying representation that can lay out that entire tree of a baggage context and support encoding of the tree and of any of the data types at the leaves of the tree. Then, with those final encoded bytes, we require a single concrete merge function that operates only on the bytes. that merge function must correctly preserve the merge semantics for the baggage context tree and all data types therein, such that when we decode it, we get the correct merged object back. In the paper, we describe a merge function that achieves this. In short, it is idempotent and order preserving, and it can correctly preserve data type specific merge semantics without having to interpret the data whatsoever. So for every single data type supported by BDL, its encoding into a baggage context can be arbitrarily merged in its encoded form. When we eventually come to decode, what we get back will reflect the correct merge of the data type at the object level. So you might ask, why go to the trouble of doing all of this in the first place? Couldn't we do some amount of interpretation of the bytes? Well, by providing a single, simple, well-founded merge function, it means the minimal requirement to be able to propagate contexts is only the atom layer. This is a very low barrier to entry. For example, implementing this in Go required less than 100 lines of code. This makes it very easy for us to support baggage propagation through many different languages and to incorporate new languages quickly. And remember, that kind of logistical issue is precisely the kind of problem faced in deploying cross-cutting tools today. So I'm only going to summarize our actual implementation and evaluation. So we implemented the tracing plane in several languages, primarily evaluating our Java and Go implementations. We presented in the paper 6 cross-cutting tools, some of them updates of existing tools, others being new tools entirely. And we deployed them across a range of distributed systems, including data analytics and microservice environments. In our evaluation, we deployed these tools side by side and showed that they can correctly propagate contexts in all of these systems. And this is done using only the generic low-level instrumentation of those 5 propagation operations. In some of these deployments, executions traversed components in different languages, demonstrating cross-language interoperability. And as a sort of final evaluation piece, we typically only add about 20% overhead compared to a static encoding of this data, so it's very efficient. So that was a whirlwind tour of baggage contexts, and if you're building a distributed system or a cross-cutting tool, we would invite you to consider using baggage contexts inside your system. And with that, I would like to thank you for your attention and invite questions.
Questions? Go.
So if a context is split into 2 concurrent branches and then later merged together, do you need to order those concurrent context branches together?
When you say order them...
Order, so basically for 2 concurrent branches, in distributed systems, unless you have vector clocks or whatever, if they don't have correlations, it's very difficult to order them. So when you merge them together, do you need, so after the merge, of course they have a causal relationship, it's easy to order, but before that, so after the contexts are split and before they are merged, there's some concurrent branches. So do you need to merge them, or there are some scenarios that you actually need to merge them?
So this is dependent on whether the baggage context itself has data added to it in those concurrent branches, and whether those data types need to preserve the fact that there is no ordering between them. So some of the data types that we have do in fact enable this, but many data types don't need it, and therefore there's no reason to do that. For example, if you're propagating a set of things, you may not care whether 2 elements of that set were added concurrently or in any particular order. And this is where the sort of flexibility with data types comes in very handy, because you can go down to the simplest and most efficient data type available to you. So yes, we can handle it if we need to.
Any other question?
All right.
Let's thank the speaker.
Yeah, I'll go speak to Chris in a second.